Hi, so in this video, we're going to see how to fit and interpret the linear regression model. So we are going to emphasize on the simple linear regression model, and future video are going to be dealing with the multiple linear regression model. So we are going to do this both theory and practice. So the next video will be more practical, how to get the coefficient, but we see how to interpret the result here. So let's say we have an equation of the form y equal to a plus bx, and in this case E is made for the error term. So the goal is to estimate A and B such that we can check whether there's indeed a linear relationship between y and x. So the A is called the y-intercept and B is a coefficient of x. Now, so if you take this particular example, so we have the car performance from 1974, and in this data set have 32 observation and 11 variable, but we are going to focus only on two variable, the gas mileage, which is in gallon, and the weight of the car. Now we are going to see whether there's a linear relationship between the weight of the car and the gas mileage. So to do that, we are going to fit a linear regression, a linear line basically. So we estimate the gas mileage with respect to the weight. So you can see that the weight is on the x-axis and the mileage is on the y-axis. So we try to fit a line that's best match this set of points. So the error term basically is, you can see that this normally for a perfect line, all these points should be lining on the line, but in this case we don't have that. But we're trying to find a way that we can put this line such that the sum of this error is minimal as possible. So the goal is to fit the line such that the error are minimal as possible. So that's what we call fit a simple linear regression model. Now, to emphasize on our particular case, we want to check whether does car weight affect gas consumption. So in this case, because our variable of interest is the gas mileage, so is in US per gallon, so it's going to be the y, and the weight is going to be our x. So we are going to try to estimate the line of the weight, the line of the gas with respect to the weight, right? So you want to find A and B in this case. And when we get A and B, there's one particular test that we're going to do here. Test whether the result that we get is indeed significant. That means we want to test to make sure that even though we get this coefficient, if this coefficient makes sense or not. So to do that, we have to test the null hypothesis to emphasize that the null hypothesis is that there's no significant linear relationship between the weight and the gas mileage. What this means is that if this B is 0, that means you're just going to have a y equal to A, right? So there's no relationship between x and y, so because this is going to give you 0. So in that case, you say that there's no significant linear relationship between y and B. And in the opposite, which is the alternative hypothesis, which is going to be there's a significant linear relationship between the two. So we are going to find, we can get this coefficient, then use the p-value, the r-square, and the f statistic to come to decide whether this result makes sense or not. So what we do is, to do that, we have to fit a linear regression model. In R, we do it using this formula because this is the gas mileage. So we want to fit the gas mileage, which is the response variable, with respect to the explanatory variable. So this is like the weight of the car, this is the gas mileage, and data G is the data set that contains this variable basically. So when you fit that, you can do the summary of the model and you get this result. So from the result, you can get the y-intercept, which is the y-intercept, which is the A. This is the A value, and this is the B. So basically, in our equation, this A and B are respectively, A is 37.28 and B is negative 34. Because this is negative, we say that they are negatively correlated. If it was positive, we say that they are positively correlated, but in this case, negative means they are negatively correlated. So the second thing is, because the null hypothesis was emphasizing on the fact that B equal to 0, so this is the B, right? and we said that this was the value for the B, and here we have the p-value that for that test statistic. So we are going to use this p-value to test whether we have to reject the null hypothesis or accept it. And there are also some information here, just the p-value that we get here, the p-value is the same as we get here. We also have the adjusted r square, and we have the multiple r square also, which is this value, but we are going to use these two, the adjusted r square and the p-value in this this model. We also have the degree of freedom and the f statistic, which in this case is 91.38. So we can also get the f statistic here. This same information we can get it from the Anova table, and also we have all this. We are going to get there. Now you can see that our p-value was this number, which is very small. The multiple r square was 0.75, which is some here, this number, and our adjusted r square was 0.7446. So in this case, if we use the significance level of 0.05, we will reject the null hypothesis because this p-value is very small, so we reject the null hypothesis with 95% confidence level. So when you reject the null hypothesis, was that there is not significant linear relationship between the wet and the gas mileage. So we reject this because the p-value is very small. So when you reject this, therefore we accept the alternative hypothesis. So because we reject that, we are going to say that we conclude HA. That means B is different than 0. That said, there's a significant linear relationship between the two, right? And also you can also use the adjusted r square. The largest the better. So the adjusted r square gives us 0.74, which is 74.46%. This exhibits a strong regression relationship between the two variables. So there's a very strong relationship between the two. And if you check the correlation coefficient, we see that it's going to be a negative number and a very high number. So it also emphasizes on this. Now, there are also some key information that you can get from the Anova table, like the f statistics. The f statistic is this number, and I'm going to compare this table basically with what we get as an output of R, so you can easily match the value of the table to what you have as an output, because you can compute this manually. There's some formula to compute this, but you don't have to memorize the formula because you have the computer available for us that can do the work, and we can just know how to interpret the result and get this information from there. And also this end, our data set, we have like 32 observations, so 32 minus 2 is just going to give of 30, and this also is going to give you some hints to match this value. Now the f statistics basically is going to be somewhere here, so it's going to be sum of square error and divided by the mean square error. So the larger value of f support the alternative. So if you have the larger value of f statistic, that means we go for the alternative, then we reject the null hypothesis. Now this is just to match some value from the table. So basically this is the sum of square total, this is the sum of square of the model, this is the sum of square error. So basically just match whatever you have to this, and you can get some information. S is the notation for sum of square, T, M, and E are notation for total, model, and error respectively. So this is the sum of square total, sum of square of the model, sum of square error. That's how you interpret it. Now this is where it's very important. You should be able to match the result to your table, because you don't want to compute this manually. So when you run the Anova table of the model, you can just type Anova of the model. This is in R, assuming that it is in R. So while you do that, you're just going to get this output, right? So from there, you can see that the first column is degree of freedom, right? So you have 1 and 30. So this one matched to this one. This 30 is because we have a 32 observation. 32 minus 2 gives you 30. So this value is going to be this one, because you see that you see that sum of square here. This is sum of square. So this corresponds to this corresponds to this corresponds to this corresponds to this, and our f statistic, the f value is 91.37, which is here what we have here. So you can see that you don't have to compute this manually, you can just get the result from the table. And also we have so let me go back. you're going to see that this same F statistic that we get here, this 91.37, we also have it from the summary table, from the summary of the data of the model, 91.38. So it round up, right? So that's what we have there. So basically, that was all that we need for. Also, we have the R square. Is explained as R square is used as explaining the fraction of variability in the data explained by the regression model. But I was mainly focusing on how to test if the coefficient of the model are significant or not, how to test if there's a significant relationship between the variable or not. So I think we did the good job here by explaining exactly what we need. So we conclude by saying that you can use the p-value, the F statistic, which is we get it from here, from the Anova table, or from the summary of the model. The summary of the model also gives you the F statistic, and you can also use the adjusted R square, which is here, right? So basically, we found 3 criteria that allow us to test for significance of this coefficient. But in this case, we found that based on our finding, we conclude that the weight of the car indeed have a huge impact on the car consumption. So that's it for this video. So the next one will be basically trying to get this result with R. So thank you, and hopefully we're going to get on next video and do that. Thanks.